Okay, in the previous example, we looked at the undamped mass spring oscillator. Okay, so we ignored any effect from the friction. And now in this example, we're going to add some friction. So we're going to add some damping to this system. In particular, we're going to set B, the damping coefficient. In this case, we're going to set it equal to 5. And let's see how that changes the dynamics. So for the undamped mass spring oscillator, we saw that the mass would just continue to bounce back and forth between its maximum to the right displacement and its maximum to the left displacement and continue to do this forever. So when we put some damping on the spring, you should expect that this behavior would likely change. So let's analyze what the solution would look like, and then we can compare that to what we might expect to happen. So now if we want to find the solution, where we're starting with an initial displacement of 1 unit to the right and no initial velocity. So we're just going to pull it 1 unit to the right and then let it go, okay, not give it any initial push or pull. So if we wanted to find the solution to this, then we would set up our auxiliary, our characteristic equation, which would be r squared, and now we're setting that b is equal to 5, and we have a spring coefficient of 4 still. So there's our characteristic equation. This has two roots, minus 4 and minus 1, right? So this factors into r plus 4 and r plus 1. So we have two distinct real roots, and we know what those solutions should look like. So that means we would get a general solution that x is c1 e to the minus 4t plus c2 e to the minus t. Okay, and then using our initial conditions over here and over here, we could solve for the undetermined, or our general constant c1 and c2 in this case. So I will kind of skip that step for the moment, but what you should find out is, and you can check this, that the coefficient in front of the e to the minus 4t is a minus 1/3, and the other coefficient is positive 4/3. Okay, so you could check that at time 0, this would actually put me at an x value of 1, and the derivative of this would indeed give me 0. Okay, and so now we've got our equation for the solution over here, and this looks quite different than the undamped solution, which had sines and cosines in it and gave us some behavior of a spring bouncing back and forth. So you wouldn't expect a solution that looks like this to bounce back and forth, and that's okay, because you wouldn't expect a spring, when we've got some friction, to bounce back and forth forever. So let's take a look at what the graph of this solution would look like. So that's over here. And these are exponential terms. So as t goes to infinity, you would expect, well, this is going to go to 0, and this is going to go to 0. So the solution x going to 0 means that this mass would actually come back to rest at its equilibrium position when x is equal to 0. So we don't get any oscillations here. That's a big important point to make. And so when we don't have any oscillation, that's because we have real roots, right? We don't get the trig functions that we get in imaginary roots. And in particular, in this case, we would say that this system is overdamped. There's so much friction that we don't get any oscillation in the mass. Okay, so now let's see what happens if we kind of decrease the amount of friction a little bit.